Okay, everybody, hello for the final time. How are you doing out there, everybody? Can you hear me okay? Am I coming in loud and clear? Hello, Kevin, Chen, Oliver, hello. So it's week 10, it's the very last tutorial. It's very sad, of course. Um, Hi, Brendan and Shakira. Um, it's very sad, but maybe you'll be on campus next year, and we might get to cross paths again or see each other again. Um, in today's tutorial, I thought we could start by looking at some matrix questions, questions about matrices. And then maybe I'll just open it up and see what you want to talk about. I think that's the most important thing today. In Monday's tutorial, I did a lot of calculus. I did improper integrals and some other things. But today, I thought we could look at things like, inverse of a matrix, transpose of a matrix, and those sorts of things, because this is the last week for tutorials. Okay, so if we don't cover them this week, then they don't get covered. Okay, so let me know what's going on in the chat, and I might just share my PDF with you. And remembering that this is a deeper understanding kind of question, tutorial. So I thought we could start with, the transpose of a matrix. Okay, so you see in this question, it's just an R question. I'll do some H questions in a minute, but let's just remind ourselves what the transpose of a matrix is, right? So with the transpose of a matrix, all we do is we swap the rows and the columns. So you can see here is row 1. That would become column 1. Here's row 2. That would become column 2. Here's row 3. That would become column 3. So let's just do one of these questions, and then we can move on to something a bit more difficult. Okay. So let me share my document camera with you. All right. So let's say if A is this matrix, right? Who can tell me on the chat what is the size of this matrix? Who can tell me? What is the size of this matrix? Okay, 3 rows and 2 columns. Yeah, thanks, Kevin. So this is a 3 by 2 matrix, okay? And to get the transpose, what you do is you change the shape, right? So this column becomes row 1. This column becomes row 2. And notice it's got 3 columns. So these numbers are reversed. Okay. So that's a pretty easy kind of question. But let's go on to something a bit more challenging, because I know this is a deeper understanding tutorial, right? So let's have a look at something more challenging. That's just to remind you of what the transpose is. Okay. So I thought we could look at 16. 16 is a H question. Show by constructing an example that A transpose times A does not equal A times A transpose, even if A is a square matrix. Okay, so what we're asking for is some kind of specific matrix A where the multiplication doesn't commute. Okay, and I think this is a hint. Think of a square matrix. Okay, so let's try to think up one of those. Let's just test some things first, right? Okay, let's choose a really basic one, and I'll just share my document camera with you. Okay. All right. So, yeah. So, give an example where A times A transpose does not equal A transpose times A. All right. So I just tried a few things. One, two, three, four. Okay, so the example that I came up with was just a 2 by 2, so it's a square matrix. If A is this, what is the transpose? Well, that goes there, this goes there. Okay, let's work out the, oh, sorry, this is not equal to, yeah, not equal to. Okay, so A times A transpose. All right, so let's remember how we multiply matrices. It's rows times columns, right? So 1 times 1 plus 2 times 2, 5. 1 times 3 plus 2 times 4, that's going to be 15. Oh, sorry, no, 8 plus 3 is 11. 3 times 1 plus 4 times 2, that's also going to be 11. 3 times 3 plus 4 times 4, so that's going to be 25. Okay, now let's look at the other way and see if that's the same or different. Okay, so 1, 3, 2, 4. 1, 2, 3, 4. Okay, let's see what happens. Okay, 1 times 1 plus 3 times 3. Well, this entry is 10. So remember, two matrices are equal if and only if the corresponding entries are equal. So this matrix cannot be equal to this matrix because this entry is different from this entry. But let's work out the other parts. 1 times 2 plus 3 times 4, so that's 2 plus 12, 14. 2 times 1 plus 4 times 3, so that's 2 plus 12, which is 14. 4 plus 16, 18. So you can see very clearly that these things are not equal. So that's a basic example, right? So can anyone give me a matrix where the multiplication does commute, where it is equal? Can anyone give me on the chat or in the on the microphone, what is an example where the multiplication does work? Can anyone give me an example? Yeah, IGN identity matrix. Can anyone give me another example? So the identity matrix is a good one, right? Because if A equals I, then the transpose is also I, and so A times A transpose equals I equals A transpose A, right? Who can give me another example where this will actually be true? Just a simple matrix. Who can give me an example? Come on, people. It's week 10. It's the last tutorial. 1111. Yes. Oliver, awesome. What about an even simpler one? Zero matrix, zero matrix. Okay, so I think there are some examples where this will work, but it's not true in general. Okay, so the point is we know that matrix multiplication doesn't commute, right? So that's the most important thing. Multiplication doesn't commute. Okay, that's the most important thing. But it is super frustrating, right? We know, we just with regular numbers, 2 times 3 equals 3 times 2. But with matrices, oh, you nasty matrices, it doesn't work. Okay, it doesn't work. Okay, so that's that's a basic example there. Let's keep going with this transpose, and we can see another example. Okay. All right. So I'm looking at question 17 now. So suppose there is a real matrix G. So that just means the entries are real numbers, such that G times G transpose is this. Now, this is a special matrix called a diagonal matrix, right? It's got numbers down the diagonal and zeros everywhere else. Prove that the diagonal entries are non-negative. So let's do that first, and then we can look at the second part of the question. Okay. So it's not a difficult question. It's only a 2 by 2 matrix. Okay. So let's introduce some notation, and then we can work it out. Yeah, Kevin. Yeah, that's right. You can swap the order, Kevin. So let me show you. So, 2 times 3 is the same as 3 times 2. That thing's the multiplication is commutative, right? It commutes. But this, no, it doesn't work. You can't say that. Okay, so you can change the order. So with matrix multiplication, order is important. Order of multiplication is very important. All right, so let's have a look at 17. Okay, so we're told assume G times G transpose is this. Okay, where G is a real valued matrix and lambda and mu are real numbers. We're asked to show that lambda and mu are positive. Okay, so any ideas on how we might tackle this one? What might be a strategy? It's just a 2 by 2 matrix. So can anyone suggest what we might do? People have got their microphones ready. You can tell me on the chat if you've got a strategy. What do people think? What do people think? If you were given this in an exam, what would you do? What might you think about? What do you think? Come on, there's 7 people here. So let's hear your suggestions. Come on, people, it's the last tutorial. Now's the time to get involved. Okay, what would be a strategy for this question? Who can tell me? Any ideas? Any ideas? What's going on? Hello, Maximilian. Let me know in the chat, people. How can we show that these things are positive? Who can make a guess or a suggestion? Come on, people. I'm not going on until I get one suggestion. At least one. Kevin has no clue. At least that's something, right? That's okay. Well, sometimes with these small 2x2 matrices, you can just let G be some, yeah, find the transpose, yeah. So Brendan, it's a good suggestion. So let's work with that. Let's work with A, B, C, D, okay? Where A, B, C, and D are real numbers. So let's work out the transpose and then multiply to get the left-hand side. And then we can compare it with the right-hand side. Okay? So this times this is this magical diagonal matrix. Okay, so let's work this out. And we know it's got to be equal to this diagonal matrix. All right, so A squared plus B squared. AC plus BD. CA plus DB. Okay, so if you look, they're the same. And then for the last one, C squared plus D squared. Okay, now for this matrix to equal a diagonal, what do we know about these two entries? They have to be 0. Okay. And A squared plus B squared equals that. And we know that that's greater than 0. Why? Because the sum of squares, right, are greater than or equal to 0. Okay? Okay, so with these small 2x2 problems, sometimes it's a good strategy to actually just write out arbitrary entries for a 2x2 matrix. Okay, and then see what happens. Okay, so are there any questions for that one? Let me know. Let me know. Can you follow the ideas? You're comparing this with this. And these two are equal if and only if the corresponding entries are equal. Okay, so the second part of this question, it says if lambda equals 45, so and mu equals 20, what is G? Okay, so try to find these values that give you these entries down here. Who can tell me what like A, B, C, and D would be? Who can tell me? You're basically solving these two equations. Any ideas? Okay, so you want to, you want these to be 0, you want that to be 45, and you want that to be 20. I'll tell you what, why don't I leave that for you guys to do? Okay? Yeah, Maximilian, yeah. Exactly. Like you've essentially got a whole bunch of simultaneous equations here. I think that's the way that you can do it. Okay? So those two things have to be equal, right? And equal to 0. So yeah, it's just going through and finding A, B, C, and D that will give you that when you multiply together. But I'll leave that for you to do. All right, so why don't we go on to the inverse of a matrix? Okay, so we've talked about transpose for about half a lesson. Why don't we talk about the inverse? Because this is a super important idea. Okay, so the inverse is like when you multiply 2 by 1/2, you get 1, right? So 1/2 is the multiplicative inverse of the number 2. So with matrices, it's a bit more complicated. So let me share the next question and we can do it together. All right. All right. So write down the inverse of each of the following matrices. Okay, so you've got these matrices and you want to find another matrix such that when you multiply them together, you get the identity. Okay, so let's just remind ourselves of what an inverse matrix is. Okay, so let me just make a quick so A inverse satisfies A times A inverse equals the identity. Okay, so if you have a matrix A and you want to compute its inverse, well, this is what it's got to be satisfied. Okay. So let's consider our first question. So A is the matrix 1, 5, 6, 0, 0, 0, 0, 0, 0. And we want to find a second matrix such that when you multiply this with the matrix, you get 0, the identity. Now remember, the identity matrix is just the diagonal is 1 and the main diagonal is 1 and all the other things are 0. Okay, so we're looking for a 3 by 3 matrix such that when you multiply by this, you get this. Okay, so what's going to happen? Well, I want to multiply this row by the first column of A inverse, and it'll give me 1. So how can I do that? Right, I want to multiply the first row by the first column of this new matrix, and I want to get 1. So the only way I'm going to do that is if the first entry is 1 and the rest are 0. Okay. Now for the second row, I want to multiply that by the second column of this matrix, and I want to get 1 in here, right? So that times that needs to add up to 1. So obviously you've got a 0 here and a 0 here. So the most important element is right there. Because 5 times 1/5 will give you 1. Okay, lastly, this row has to multiply by the third column and give you 1. So 0, 0, and 6 times something has to give you 1. So it's going to be 0, 0, 1/6. Okay, so that is your inverse matrix. Shall we check? That times that gives that. That times that gives that. That times that gives that. Okay? Let's do it the other way around. Let's do it this way. Does it give you the identity? Okay? That row times that column gives you 1. That row times that column gives you 1. That row times that column gives you 1. Everything else is 0. So we're happy. Okay? So this is, this is not easy to do, but when you have a diagonal matrix, you can see all you do is you flip or invert the diagonal entries. So for example, if I had the matrix 1, 2, 3, the inverse would be 1, 1/2, 1/3. Okay, so that's a pretty handy thing to know. Okay, questions for that one. This is quite rare that you get a beautiful matrix like this and you have to compute the inverse. Usually they you do other things, okay, with other more general problems. But it's nice to know because you can save yourself a lot of calculation. Okay, let's move on to some of the properties of inverse functions or inverse matrices. Okay, so I'll just go back to my PDF. Okay. Now this is a routine question, but I think it's an important one because in the final exam, you'll see things like this all the time, these little, matrix algebra type of questions. Okay, so I thought we could have a look at 24 and then move on to maybe 25, which is a bit harder. Okay, so I'm just telling you that these type of questions are very common in past exams. Okay, so simplify this expression and then find this for specific A inverse and B. So let's do that, and then we can move on to something a little bit more challenging. All right. So 24. Okay, so we have B inverse A inverse, and we're asked to simplify that. Now, one of the things with inverse, you can distribute it, but you change the order. So it's A inverse, B inverse, inverse. Okay? So that's one of the weird things with inverses and transposes. You can distribute them into products, but you change the order of the products. Okay, so you don't know what A inverse is, but who can tell me on the chat what is B inverse inverse? Correct, Kevin. Okay, so that's the simplest that you can get it. All right. So let's do part B. Okay, so what is this? Well, we can write it like this. That's an inverse. So it's just this matrix times this matrix. Okay, so now, in order to do this, we multiply the rows on the left with the columns on the right. Okay, like a dot product. Yep. So that times that will give us the top left entry. So 1 plus 0 plus 1 is 2. That row times that column. 0, 4, 0, 1, 0, 3. That row times that column will give us that one. So 0, 0, 1. That row times that column, 0, negative 2, 0. That row times that column, 0, 0, 3. And finally, that row times that row times that row times that will give us the bottom three. And because it's a 0, it's 0, 0, 1, it's just going to be 1, 0, 3. Okay. So there you go. So that was a pretty easy one, but it did draw on the idea of matrix algebra and simplifying the inverse operation. Okay. So that's our final answer. Now, what's the significance of doing that? Well, of course, it's easier to compute this than this, okay? Because we'd have to compute the inverse of B and get A and then take the inverse of the product. This thing is much easier here. Okay. Let's do one more. And then I think I might finish the recording and we can talk sort of off camera if you want. So let's have a look at 25. All right. So 25 is an interesting one. Prove this identity for any invertible matrix A. So the transpose of the inverse is the inverse of the transpose. And then they're asking us to simplify some sort of expressions there. Okay. So 25 looks hard because you might be thinking, well, I don't know what the matrix A is, but it doesn't matter for this one. You can just do it without knowing. So let's have a look at how we do it. It's a really interesting question, I think. Okay, so it comes back to essentially this definition back here of what it means for a matrix to be the inverse of another matrix. Okay, so we're going to use that. So, yep. So we want to prove the inverse of the transpose equals the transpose of the inverse. Okay. All right. So the question is, let's start with the left-hand side. Do we have... So basically we're saying, do we have this? Okay. So you can see that's gone in down there, right? So if this is actually true, this whole thing must be the inverse of the transpose. Okay, so let's start with something concrete. If I have this, if I multiply the inverse by a matrix A, I know I get the identity. Let's take the transpose of both sides and see what happens. Okay. So let's take the transpose of both sides here. Now the transpose of the identity is just the identity, and we can distribute this thing in by this product. Thank you, don't like that. Okay, so let's do this. You change the order. Yep. So what does this mean? This means this matrix here, the product is the identity, right? That must be the inverse of this. Okay. Now, I've only done it one way in this example. You can do this the other way as well. Okay. So you just change the order here. Sorry, A times A inverse equals I, and you take the transpose of both sides. Right? Distribute the transpose and change the order. Okay, so this is one way to get the identity. This is the other way to get the identity. So this must be jointly equal to it. Okay, so we started with something concrete. We took the transpose and then we realized, oh, that actually satisfies the definition or the original relationship that we were hoping to get. Okay, quite abstract, but hopefully you can just see we're applying the transpose law and the definition of what it means to be an inverse function. All right, so let's do the last part of this question, and then we can have a bit of a chat. All right, so this is 25B. So we want to simplify this. Okay, and so the easiest way is to distribute this transpose sign. And so it will be, you change the order. So it'll be A transpose times B transpose. Okay. And then who can tell me on the chat, what is A transpose transpose? Who can tell me? What is A transpose transpose? How can I simplify that? Kevin, yes, you rule. You too, Maximilian, thank you. And what is A inverse times A? That's just the identity. And so that's as simple as you can get it. You can't simplify it anymore unless you know some special relationship between B transpose and B. Okay, that's it. All right, what about the second part of this question? A little bit harder maybe. So it's A transpose C A transpose inverse C transpose. Oh my goodness. All right. This is the very last question for this tutorial. Okay. So let's distribute the inverse sign. Okay. So it's A transpose. Change the order. Okay. Now, what is the product of these two things? Who can tell me in the chat? What is the product? Yeah, it's the identity. Yeah, that's all right. So C inverse C transpose. Now there's nothing you can do more to this. That's it. That is it. Okay. Now trust me, you see questions like this all the time in the final exam. A little bit of matrix algebra. Okay, and so the most important things for these kind of questions is A B transpose equals B transpose A transpose, and AB inverse equals B inverse A inverse. Okay. Okay, folks, well, that is it. We have a few more minutes now, and I'm going to turn off the recording if you want to have a chat or just say goodbye or something. Really enjoyed these tutorials. I hope you have too. And I hope that some time in the future that we can maybe meet on the campus, maybe next year. But good luck with whatever you're doing. And yeah, I hope to hear from you in the future. And good luck with the exam. You can do it. So if you have any extra questions, let me know, okay? But good luck and goodbye. And I'll just turn off the recording if you want to have a chat. Everyone can turn their mics on if they want to. So great job, Brandon, Oliver, Kevin, Brendan, yeah, Maximilian, Shakira, Menglu Aichan. All the best, okay? I wish you all the best. So let me turn off the recording and we can have